In this video, we're going to explore a test for a basis. So given a set of vectors, v1 through vn in Rm, how can we tell if that set is a basis? We need to check if that set is spans Rm and if it's linearly independent. Now, we have looked into checking for these things kind of individually in previous sections in the course and previous videos, but there are some quicker checks for a basis that don't necessarily require you to go through all the steps that you might if you were individually checking for spanning and linear independence. And the first thing we might do is form the matrix whose columns are given by those vectors. And so we know that the span of a set of vectors equals Rm if and only if that matrix A, whose columns are given by those vectors, has a pivot position in every row. That is something we studied in a previous section. We also know that that set v1 through vn is linearly independent if and only if that matrix A, again, whose columns are consist of the vectors in the set, has a pivot position in every column. So putting those two things together, therefore, the set v1 through vn forms a basis if and only if A, the matrix formed with the columns of those vectors in the set, has both a pivot in every row and a pivot in every column. This means that A must be row equivalent to the identity matrix. And it also means that A must be a square matrix because the only way to be row equivalent to the identity is to be a square, and the only way to have a pivot in every row and every column is to be a square matrix. Okay, so how many vectors are in this basis? If A is row equivalent to I, then A has a pivot position in every row and column. Therefore, as I mentioned earlier, A must have the same number of rows as columns. A basis for Rm must contain exactly m vectors. For example, a basis for R23 must contain exactly 23 vectors. To show you some quick examples here, if we were to consider R3, if we looked at the vectors just 1, 0, 0, 0, 1, 0, okay, these vectors do not span all of R3. If we look at that matrix whose columns are formed with those vectors, we could see that we do not have a pivot in the third row, and so we don't have spanning, and the set of vectors is not a basis. If we looked at the set 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, okay, then, form that matrix. Okay, now we don't have a pivot in every column, right? Our fourth column here does not have a pivot, so these vectors are not linearly independent and cannot form a basis for R3, even though they span all of R3. So we do need a pivot in every row and column, and therefore the same number of rows as columns. So for R3, we're going to need exactly 3 vectors. Okay, so here's that all written up in a proposition. A set of vectors forms a basis for Rm if and only if the matrix A, which consists of the vectors as its columns, is row equivalent to the identity matrix. Therefore, there must be exactly m vectors in a basis for Rm. And kind of furthermore here, the additional thing we can say is that any m linearly independent vectors form a basis for Rm. We could say the same thing for spanning, right? So any m vectors that span all of Rm form a basis for Rm. So we really only need to check one of these once we have the right number of vectors, and actually checking either of them is the same thing as basically just putting these vectors in a matrix, row reducing that matrix to see if that is row equivalent to the identity. And I'll point out here that this is the type of thing we've already done in a section in this course where we were sort of checking to see if our matrix was row equivalent to the identity, namely when we were looking at whether or not our matrix was invertible. So there's a connection being formed here potentially between when a matrix is invertible and when its columns form a basis for the given set for the given space Rm, depending on the size of that matrix. Okay. So again, a quick test, and I just alluded to this. The set V1 through Vm is a basis for Rm if and only if A is row equivalent to I, where A is the matrix whose columns are given by those vectors. Let's look at a few examples. We've got some vectors in R3, and there's a question, do these vectors form a basis for R3? We should almost immediately be able to tell that no, this set does not form a basis for R3. How can we tell? Well, we know we need 3 vectors in order to form a basis for R3. And so we only have 2. So immediately the answer is no, we don't have enough. We know that there's no way we could get spanning, and we could attempt to row reduce this. There's no way we get the identity. So I'm not even going to go through that work. Here we've got 3 vectors, and we have sort of more of a chance here at this set forming a basis. We would need to, I think, check to see if the matrix whose columns consist of these vectors row reduces to the identity, and can just use some technology, Sage or our calculator or something like that, to row reduce this, or we could row reduce it by hand, but more quickly here. If we row reduce this, we would find that this is, in reducer echelon form, the matrix 1, 0, 0, 0, 1, 1, 0, 0, 0. And so we do not have a pivot in that third column, nor do we have a pivot in that third row. So we have neither spanning nor linear independence, so no basis. On a sort of simpler way of telling that, this is not row equivalent to the identity. Another example of 3 vectors in R3, again, put those vectors as the columns of the matrix, and then either do this by hand or use technology or a calculator, row reduce this. We would see that this is, in fact, row equivalent to the identity. So yes, this set of vectors does form a basis for R3. And then last example here, 4 vectors in R3. Again, we can immediately say, no, these vectors do not form a basis for R3. And if we were to, row reduce that matrix, we would know, we could sort of show that and do it, but we would know that, even if we had a pivot in every row, we couldn't get a pivot in every column. And that is exactly what turns out to happen. If you were to row reduce this, you would find that these are our 3 pivot positions. This 4th column does not contain a pivot, and so these are not linearly independent, even though they would span all of R3, not linearly independent, and so do not form a basis for R3. So kind of the easiest way to determine if a set of vectors forms a basis for Rm is to put those vectors into a matrix, row reduce that matrix, and check if it is row equivalent to the identity. That is, of course, assuming the number is right. If you're dealing with Rm and you don't have exactly m vectors, then you can immediately say no. Now, you might want to expand on that. If you have too many vectors or not enough vectors, then you might be dealing with a case where, if you don't have enough, if you have less than m, then your set would not be able to span all of Rm. If you have too many, if you have more than m, then they would be linearly dependent. And so we sort of fail in one of those accounts. If you have exactly m, then you should row reduce that matrix and see if it is row equivalent to the identity. And that will tell you if your set is a basis for Rn.